Okay, so very good evening to one and all. Thank you, sir, for being in the audience. So, I am going to talk about holographic interferometry. For last 2 days, you have been hearing the basic types of the holography and basic stuff related to Fourier optics. So, in holography, it is always said that it is a two-step process. Modulation and demodulation, what Yasin sir was telling you yesterday. So we have the recording and reconstruction. So what I am going to talk about, I have taken the sources material from this book, Basics of Holography by Professor Prof Nishchal. So if you need, I can share this book, copy of this book with you. An Indian author who migrated to Australia, and this book is treated as a Bible in holography. Very basic, a very good book, very thin book, very comprehensively mentioned. So, what is holographic interferometry? As you know, the interferometry, we all know that you have to have the reference beam and object beam. So, like automatically we write OXY plus RXY, you take the mod square, you have 4 terms, mod of OXY plus mod of RXY whole square, and plus you have O conjugate R and R conjugate O. These are the 4 terms what we always achieve. So in holography we record these interference pattern, those 4 terms, O cross R, on a film. Or in digital holography, this is what we will be recording on a camera. Now in holography, as it is possible that we can capture this wavefront and reconstruct the wavefront at a later time. So as a result, this interferometric technique can be used to compare 2 wavefronts. We have one wavefront, we have recorded one wavefront, and we can record another wavefront and we can compare them. So it is basically one interferogram and you are recording another interferogram, and then you are comparing these 2 interferograms. So this originally it is separated in time or space or even wavefronts of different wavelengths, they can be compared. So since a hologram reconstructs shape of an object with a rough surface faithfully, slides.
स्लाइड सब को मेल में मिलेगा?
हाँ, सब मेल में। So what I have written is that since a hologram reconstructs shape of an object with a rough surface faithfully down to its smallest details, large scale changes in the shape of almost any object can be measured with the interferometric techniques. As you know, the basic approach of this holography is for measuring the phase. So we'll talk more on this topic and as the time progresses. But in holography, we have the only one technique to record phase or to measure phase is the interferometric technique. And this what is the holography, we measure the phase values. Once you record the phase values, there are some statements I might have talked about, and it is in general also said that if you take a hologram, break it into 4 pieces, each piece will give you the same information. Because it is interference pattern, it has another depth of vision. If you take a hologram, focus in different regions, I'll show you maybe another class that you can focus in one simple hologram, you can focus different regions. Similarly, in digital holography, you change the depth of this distance, small d, and you can focus different parts. So here, this holographic interferometry can be used in non-destructive testing, because what is important, we can compare two wavefronts. Holography is all about wavefront measurement. So you can have one wavefront, you can have another wavefront, and then you can compare them. Two fringe patterns, basically comparing two fringe patterns, two interference patterns. Then where we can use them. So application is non-destructive testing. What does it mean, non-destructive testing? Means when you are testing something, when you are measuring something, you are not altering the object. Object is not touched upon. You are simply throwing the light and you are measuring that. So the scattered wave you are capturing. So non-destructive testing, aerodynamics, heat transfer, plasma diagnostics, as well as in the studies of the behavior of anatomical structures, prosthesis under stress. These are the various applications where it can be used. So what is the basic physics? So first we should understand what is the basic holography, because these are the equations I will be using there. So simple, this is the off-axis holography. You have the reference wave, here is the object wave which is at some angle theta. So this is how we represent the simple plane wave reference beam. This represents the object wave. So for recording the interference means we have this Rxy plus Oxy and you take mod square of that. What you record is the intensity, so it is basically mod square. You can write the same thing, Rxy plus Oxy multiplied by conjugate of Rxy plus Oxy. And when you multiply these 4 terms, take mod square, so you have mod square of this one plus mod square of this one, and then you have conjugate of this multiplied by this and conjugate of this multiplied by this. So these are basically the 4 terms. R square plus O mod square plus RO, these are the phase factors, then RO and exponential, these are the phase factors. So in a way, it can be simply written as R square, it can be simply written as OX square, and these are the phase functions. This is what we measure when we record interference pattern. So what does it mean? It means amplitude and phase of the object wave are encoded. The amplitude and phase of the object wave have been encoded as amplitude and phase modulation. This is what has been modulated. Of a set of interference fringes equivalent to carrier with a spatial frequency of this one. Now, what we do, so once you have recorded, this is the recording of the hologram. Once you have done this recording, okay. Now for reconstruction, what we do? We have the 4 terms. So as we know that for reconstruction, we have to multiply the hologram with the reference wave, or you have to illuminate the hologram with that same reference wave what we have used during recording. So Rxy we have to again apply. So that will have some transmittance value, and this is what it is written with this term. So this is what we will be obtaining when you have you are trying to reconstruct. Second term. So where we have this T naught sigma T naught prime, and this term is basically a constant background transmittance. It will be introduced.
So is the notation same with PV?
Yeah, same. Yeah.
Okay.
So I have taken the same expressions from that here in this book. So when this hologram is illuminated once again, now we have recorded one hologram. This hologram is going to be illuminated once again with the original reference beam. So we have one hologram, now we are illuminating that with the same reference beam. So the complex amplitude of the transmitted wave what we are going to obtain in the output, this is what we'll have. Uxy will be Rxy plus Txy. So Txy I am multiplying with the same reference beam. If you expand, this is what the expression is going to have. So what is real time? What is the application now? That's the basic what I just said. So what I have said so far, you have R term, reference plus object, added them together and you calculated the intensity. In an optical holography, you are taking the intensity, you are recording the interference pattern on the film. So you will have basically 4 terms, multiplying with that you have recorded once the hologram. Now you are multiplying or illuminating that hologram with the same reference beam again. So if a hologram is replaced, so this is what is basically holographic interferometry. So if you replace that hologram once you have recorded, is replaced in its original position in the same optical system to record it and illuminated with the original reference wave, it reconstructs the original object wave. Getting my point? Let me read it again. If a hologram, whatever hologram we have recorded, is replaced in its original position again in the same optical system to record it and illuminate it with the original reference wave, the same Rxy, it reconstructs the original object wave. So what? Then the shape of the object, if the shape of the object is changed, like some object has moved or it has been oriented or it has been tilted or anything has happened in between. So any such changes that will reflect into the change in the phase. So it is directly transmitted object will interfere with the reconstructed object to produce the fringe pattern, and this is what is you can see here. So this was the original image. It is a deformed object. So whatever deformation has taken place, accordingly you are going to have that changes in the fringe pattern. So we have one hologram recorded. In between something has changed, some deformation has happened. Then you are recording it again, multiplying with the same phase pattern, same reference beam.
So what are these black and white streaks?
Yeah, that shows the deformation. This is an object and it is the deformation has taken place. So what we have recorded one interference pattern, then some deformation has happened and you are using the same hologram. So whatever, how much deformation has happened, that has also been recorded. So you have now two different interference patterns, and that we can compare and come up with the what all has happened, how much was the deformation, how it has happened. So you have two states basically. One state not deformed, second state some deformation has happened. You have one interference pattern, you have another interference, and then you can compare them. Once you compare them, then how much is the deformation, that you can measure.
Any particular value of information, sir, from first stage to second stage?
So that depends how much you are measuring. So it depends from application to application. So it has the property you can measure that deformation. And that is why these are the applications. So if the changes in shape of the object are small, this is what answers your question. So only phase of the object wave is modified. Complex amplitude and wave from the deformed object can be written as, this is the modification in the phase. So you have the OXY and this is the phase change. So now get back to the four terms usually written in the book, U1 plus U2 and U1 and U2 conjugate. So the first term is there, and this much is the transmittance with the deformation. U2 is this one with the original object wave. So what will happen now? It means now we are having these two wave patterns, wavefronts, and we are adding them together. So you have U1 xy plus U2 xy, and then you are taking modest 1. So now this is a new hologram. We started with the one hologram. Now we have one hologram, and with that we have second hologram. Yes.
Sir, here we talk about deformation. So is it the change of the physical shape of the object?
Yeah,
or
physical shape of
we
the object.
consider the change of the orientation of the object.
Everything. I'll show you. There are many geometries where you can use for different types of objects and different cases. So here one deformation I am showing. So now we have two these wavefronts. Take modest square. So we are having a new hologram now. So if you expand them, this is what the expression we are going to obtain. Now here, this beta is negative, so dark fringes are seen. It depends upon this pi xy, how much is the phase. It is twice m pi, where m is an integer. So interference fringes obtained by this technique, it can be used to study changes in the shape of the object in real time. So one change I showed, that deformation has happened. Any such changes can be observed. So you have to have, basically the simple thing is, you are comparing two interference patterns or two holograms. Because the first hologram has the information from the original aspect, original position, and second one is with the deformation. So how much is the deformation, that we can measure. And this is a setup. Now here is the problem, that you have to replace that hologram in its original position, and then you have to record another hologram. So that posed a very difficult problem, and this what has been shown here. I can cite you the reference. This system for real-time holographic interferometry. Hologram is processed in situ, means the same place, and interference fringes are viewed through a CCTV, closed circuit television. Now here what is important, you have to have the hologram, and that hologram has to be in real time reconstructed in a way. So that poses the problem, and that creates difficulty, that offers difficulty, that what we can do. So it has some disadvantage also, that if you have some intermediate changes, so you have one change, one object is tilted, so in between the tilt, there are some intermediate states. So those intermediate states cannot be measured in this one. One you will measure the initial one and the final one. So this is a disadvantage with this one, but there are techniques how those disadvantages can also be resolved. So this is the real-time holographic interferometry. You have the recording, this is the laser, this is the object at rest. You capture on the photographic plate, and for reconstruction, this is the developed hologram, and then you can see the deformation in the object. So observer sees any deformation of the object that is in the scale of lambda in terms of wavelength only, very minute changes. In real time, as interference between real object and holographic image of the object at rest. So is that clear? The basic holographic interferometry, basically it means we are comparing two holograms. One is corresponding to the object in rest position, second one in the object with the deformed position. But what I mentioned here, that intermediate states cannot be measured in this way. We have to have different technique for that. Is that clear? So these are the problems basically, that you have to have replace the films exactly at the same original location. If you do not replace it with the original location, then that will give you a wrong result. Or the measurement what you are going to at the end, that will have some disadvantage or difficulty. Film developed at site. Whatever hologram you are recording, that has to be developed at site. You cannot take it to a dark room. So you have different tools and techniques for that. Emulsion pre-swelled before exposure. Now here, this can be removed, this technical problem related to the exposure can be removed or overcome with the help of digital holography. In digital holography, you can do the reconstruction in real time. So these are the problems with the optical holography, when you are recording on the hologram on a film and then you are doing that. So it becomes easier when you are comparing and doing it with the digital holography. Digital holography, you can do the reconstruction in real time. There are fast algorithms and then you can do that. Maybe in one of the lectures when I will talk more on the application side, there are some holographic, digital holographic microscopes available across the world, commercially available, one can buy. The cost is of course very high. It costs around I think more than 1.5 crore in Indian rupees. So I have used some of the such microscopes. I will show you some results also. That can be used for real-time monitoring. And
So is this type of microscope available in India?
no, there is no such microscope available in India. I wanted to buy at one point of time, but I didn't get the fund. But I have used that digital holographic microscopy, and you will see very good quality 3D images on the screen. And it has been used for basically for the cancer cell detection. I have used one in the Finland. Yeah, they have developed a holographic microscopy, but the quality is much different. What is available from that Switzerland.
So in the previous stages, you said that we cannot observe the intermediates.
Yes.
But what if we just take 5 different slides and my deformation has to be gradually shifted? Then we would be able to observe.
Yes. So I have not come to the solution to that problem. I just posed you that these are the problems associated with this one. So to make you understand that what is holographic interferometry. Now then we have another solution, another type of holographic interferometry that we call as the double exposure interferometry. What is this double exposure interferometry? So it is possible to record 2 holograms on same photographic plate. You are not developing the holographic plate. You are recording 2 holograms on the same holographic plates. One of the object in its original state and other of the deformed object. Getting my point? You are recording 2 holograms on the same plate, one of the object in rest, another one with the deformation. So what is the benefit of doing it? Benefit is you don't have to develop the hologram. You can develop once we have recorded both the holograms. So in the previous case I mentioned you have to have developed the hologram, it has to be replaced at the same location and then you have to illuminate it with the reference beam. So what is done here? Here you don't have to develop them, you are recording 2 holograms together simultaneously on the same photographic plate, one with the object in rest, another one with deformation. So this is what we call as the double exposure. So you are exposing the object twice, doubly. One in rest, another one with deformation.
So one of them serves as a reference beam, or we have
Reference beam will be same. You have set everything. You have the object B, reference beam. You have recorded the interference pattern. Now you move the object, whatever deformation you are given. So you can move the object and again same reference beam and record it again on the same holographic plate. This is what we call as the double exposure interferometry. So the object has been exposed twice. Yes.
So wouldn't that affect the interference pattern of the first one?
No. First one is recorded. It is not going to affect that. Now you record the second one. Right?
So even in the primordial case in which the first case, is there a compulsion of using the same reference beam?
Yes. It is always compulsion.
Okay, sir.
It is always. That compulsion will be removed only when you are using a rainbow hologram or other holograms. Maybe there was one industry fellow yesterday, he brought some holograms also. I'll ask him to bring and show you again those holograms. Those holograms you can see in the sunlight, but for recording they have used the laser light. For reconstruction, like for seeing the image, you don't need those laser beams. Means you, for reconstruction you are able to do with the sunlight or this normal light. So what is happening here? You have this OXY object and deformed object O prime XY, and you are recording this interference pattern. So O prime XY you can write with this one because it has some deformation in terms of the phase. So what would be the intensity? Intensity will be this one. And this,
But sir, you have to mention their del phi, but some angle which is to rotate there during the deformation.
so that if in case you are taking the tilt,
Yeah.
if you are tilting the object, then you have to consider that.
Yeah.
So deformation can be of any type.
Yeah.
Tilt is a very important or very good application and very useful research topic for the digital holography. So if you are tilting the object, how it is going to affect and how you can do that. Here I am generally taking some deformation, not talking especially about the tilt. I will show you one of the examples also. So what will happen in this case? The bright fringes are seen when this phase difference is equal to twice m pi, where m is an integer. So double exposure interferometry, it has the advantage that repositioning of hologram is not critical. You are not repositioning that hologram, you are not developing, not repositioning. Since two interfering waves are always reconstructed in exact register, in addition, visibility of fringes is good, since two waves have same polarization and same amplitude. So it gives you better result. It has a common problem again. So what is that common problem? These are what all I am talking, these are all research problems and there have been research papers to solve them also. So common problem is that if you are using a continuous wave laser, it is unwanted movement of the object between two exposures that poses a problem. So some types of object motion can be eliminated by, this is the solution again. So this is the problem with the CW laser, how to solve them. So for solution, use the object motion and take the reflected reference beam from a mirror attached to the object. So that compensates the error. Alternate technique is hologram plate can be attached to the object and the doubly exposed reflection hologram can be again recorded with the object illumination through that hologram plate. So these are the solutions of such problems. It has a disadvantage, again in this case, similar to which is inherent to the holographic interferometry, that information on intermediate states of object is not available. Again we are taking one state and the initial state and the final state. So in addition, control of fringes to compensate for rigid body motion and avoid ambiguities, these are not possible here. Then in this series, for holographic interferometry, we have a technique called sandwiched hologram. It means you are taking two holograms, sandwich them together, you have this object and this is the first exposure. Then you can see some tilt here. It is what you are asking for the angular tilt. So it has been introduced some tilt, so you can see the tilt how much it is. So that is with the second exposure. Now this is what reconstruction with fringes you can see, and the tilt also. Object tilt compensated, fringe free reconstruction what you can see here. So these are different techniques for compensating them in the holographic interferometry. Is that clear? one general, very famous kind of picture you will find in the books and Google also. So movement in phase has been contoured using holographic interferometry. Fringe spacing represents a movement of 30 micron and was created by 2 pulses from a ruby laser. Here, a pulse laser was used, not a continuous wave laser, because continuous wave laser posed that problem. So to solve that, this is what has been used. And the movement is 30 micron. So this is what we can measure with the holographic interferometry.
But pulse laser will be used there also. Pulse laser is possible.
Yes.
So you are saying that ruby laser is.
Yeah, that is a pulse laser. So double exposure holographic interferometry, again the same thing what all I have explained. So 2 successive holograms, first exposure object is in some reference state, second exposure object is moved or deformed, and when we talk of deformation it can be of any type, tail, some movement, displacement, everything. So during reconstruction the 2 images interfere as though they were 2 copies of the object. So if conditions at the recordings are different, so interference path between the reconstructed holographic images reveals the deformation. Again, in principle, in nutshell, the whole process, if you try to understand, it is very simple. We have one function, one fringe pattern, another fringe pattern, and you are taking the difference between these 2. But we have to have this setup to record the interference pattern, and then you are able to calculate that.
Sir,
Yes.
what is the difference between interferometric fringes and Moire fringes?
Moire fringes. Moire fringes is different thing. You have seen that nets in the windows. In the windows to not allow the mosquitoes to come inside, people use nets. Have you seen them? So you take 2 pieces of net, one or put one over the other and simply change that. You will see a kind of pattern. So that is a kind of Moire pattern. That Moire pattern you can optically generate with the help of this Fresnel diffraction. If you solve those problems what Sir was talking for the Fresnel pattern, you will get those Moire patterns. That is again a kind of imaging. That is also the imaging property. You can generate the image also. So, but that is not the interference pattern. It is simply 2 patterns overlap each other that creates that kind of pattern. It is not at all interference.
And you can see Moire pattern also when you record on the CCD camera. If you record fringes on the CCD camera, you will see Moire pattern.
You will see Moire pattern, yes. So it is not interference. It is not interference.
So sir, the basic condition of interference is not mandatory in the case of Moire pattern?
No, it is not at all interference. So why the conditions of interference will be applied? So for interference pattern, of course, the basic interferometry, you have to understand that the 2 waves to interfere, they should be in the constant phase difference, then they have to maintain, there should be the coherent monochromatic wavelengths, same wavelength, same state of polarization. That is very important. If you have one wavefront, another wavefront, if they are not at same state of polarization, they will never interfere. And that is why when we use send information in our fiber optic cables, we are able to send them because 2 photons never interact. To have the interaction, you have lots of conditions. But 2 electrons, if you want to send, they are going to interact. And this is where the A's photonics has over the electronics. Okay? So these are some more examples of that holographic interferometry. You have this laser light here, you have the reference beam, you create the disturbance, and this is how you can see the patterns and measure them. So what are the geometries? For different kinds of applications you have to have, and what you are to measure, you have to have different geometries. But one thing is important, this is all important in the optical holography when you want to record it on the film. But the benefit now is in the digital holography, you are not recording anything on the film. So you are recording the interference pattern on the camera, and then you are numerically reconstructing them. So for any kinds of application, what all you want to do, you have to numerically compensate them. So I was talking in the morning also, in the afternoon class also, that Fresnel algorithm for reconstruction. So you have to have the sampling, write that algorithm for reconstruction. You can create all kinds of holograms. Maybe Fourier hologram is the very easiest way to calculate. Simply take the Fourier transform of the object and use with the reference beam. I think this also you should take as the assignment. Simple for the recording and reconstructing Fourier hologram, recording and reconstructing fractional Fresnel hologram. You can use again fractional Fourier transform and record a fractional hologram, like that. So here again you can use different geometries. That is the tail. So during exposure of the double exposure hologram, this is the enlarged view of a portion of the bar showing the displacement in more detail. So how much is the displacement, that you can very well measure. So these are the applications where this holographic interferometry is used. So then we have another holographic interferometry that we call as the time average holographic interferometry. So it's almost going to be 5 and Dr. Utpal has come. So I have to have his talk now. So anyway, I'll finish quickly now. So time average holographic interferometry, this is the vibrating object here. So what we do here, that hologram is recorded of the vibrating surface with an exposure time which is long compared to the period of vibration. If it is something is vibrating, like you can see this guitar is vibrating. So what has to be done? Exposure time has to be larger, longer than the time of vibration, period of vibration.
In this technique, take single exposure, double exposure.
You can take all. And here you have to do the time average. You have to record many and then you have to average them. So exposure over several time periods. So you have to have exposures on several time periods and then you have to record them. Reconstruction and reconstruction, interference of the extremum positions, it is simple to carry out. This is what we call as the time average, because you are allowing it for several time periods. That is why it is called time average holographic interferometry.
So what is the basic difference between these two pictures?
The harmonic notes.
Yeah, notes, which you have created the vibrations. So again, one in the rest, another one is in the deform. So this vibration again is a kind of deformation. You are listening good music, but it is a kind of deformation because it was in the rest and you have deformed it. Oh, that is all. So I'll stop here. Maybe Dr. Utpal has come. Any questions?
In the last image, so that essentially depends on which string I pluck.
Yes, yes. Of course. This is a very famous picture. You will see in many books.
Yes.
This one. This is the one. You will see in many books. So I'll continue more on this holographic interferometry tomorrow, and then tomorrow we will start the phase shifting digital holography. Sir has already introduced the topic, and then we will continue. So then my more stress will be on the application part of the holography, on the digital holography. So learn more basics from sir. I will talk more on the applications part. Okay?
And
And
I will also maybe tomorrow after Dr. Nishchal finishes this part, I will also show similar application but using a photorefractive crystal.
Yes.
So if you use photorefractive crystal, deformation of an aircraft in a wind tunnel. It's a practical application. So I'll show you some pictures.
So आप आ जाइए ऊपर मैं जाऊँ
Yes.
आप टेंडली और आप जाओ
There was a,
ये लोग टायर्ड हो गए होंगे पनिशमेंट दे रहे हैं लोग They have come here to be tired.
Yes, yes, yes. And our duty is to make you tired.
Gladly.
there was a method which was traditional charge
Yes, sir.
method, where some dust particle was used to